back when we were talking about joint probability distribution functions, we talked about how it would be nice to have some kind of measure to help us understand the association between x and y when we only had two random variables. So for example, do large values of x tend to occur with large values of y? Or maybe do large values of x tend to occur with small values of y and vice versa? It would be nice through the use of a probability distribution function if we could actually quantify that so we get a better idea of the relationship or the association or the dependence between random variables. And the way that we can do that is to use a statistical measure known as the covariance. Now, the name covariance comes about through, as you will see in our expected value expression for it, you're going to see some similarities to the variance expression. And the co comes about because we are looking at, in this case, two random variables at the same time. So to help set this up a little bit more, let's take a look at some plots. So imagine we have a very small population and we have our variables of interest, or characteristics of interest, are denoted by x and y. And here's a plot of their corresponding numerical values. And what we see in this particular plot is that large values of x tend to occur with large values of y, and small values of x tend to occur with small values of y. And because of that, we see that we have dependence between x and y. As x changes, y tends to change. And it's also this is also referred to a specific kind of dependence called positive dependence as well, meaning as what happens to x, we expect the same thing to occur with y in terms of large with large, small with small, and so on. Now, one could also have a population that looks like this. In this particular case, large values of x tend to occur with small values of y, and small values of x tend to occur with large values of y. And so again, we do have dependence, and this type of dependence is often referred to as negative dependence. Another way to think about why we have positive or negative in terms of that wording, if I were to draw a line that goes through the middle of these points, we see that we have a negative slope. So that's why it's referred to as negative dependence. Okay. Now here's a question then. Suppose that we have no dependence, or in other words, independence between x and y. What would then this corresponding plot look like? Let me do some erasing here. Well, in that particular case, basically that means that there's no association between x. So I don't care what x is, y is just going to do its own thing, and vice versa. So in that particular case, you would expect to see something like this, just simply a random scattering of points. That would be no dependence, or a more concise way to put it, independence. So let's relate this to the high school and college GPA example that we've talked about a few times already. Suppose I let x be a student's high school GPA, y be a student's college GPA. Now, generally speaking, we would expect there to be dependence, because after all, high school, or at least one of the purposes of high school, is meant to prepare one for college. So the better you prepare in high school, the better you tend to perform than in college. And the kind of dependence that we would expect is positive dependence as well. So as, let's say, maybe let me restate that. So as x, the high school GPA, as I have higher and higher and higher value of those high school GPAs, I would tend to have higher and higher and higher college GPAs as well. And the reverse would be true too. The smaller the high school GPA, the smaller the college GPA. This is what you would expect. It doesn't mean every single individual will follow that exact same pattern, but you would expect on average, notice the word average there, notice how I'm also using the word expect, you would expect that on average, this kind of association to occur. So the statistical measure that's used to measure that association, again, is referred to as the covariance. There's a number of ways to symbolically denote it. One way is to use the Greek letter sigma again, like we did with the variance and standard deviation. but now we put a subscript x and y. Another way to denote then this symbolically is with the word cov, x, comma, y, for covariance. Now the way this numerical measure works, it's going to be an expected value, you'll see it shortly. When the covariance is equal to 0, that means essentially you do have independence. When the covariance is greater than 0, that means you have positive dependence. And when the covariance is less than 0, it means you have negative dependence. Go back to some of those previous plots that I just showed you and relate those symbols, those meanings, to what the plots are showing you. And the further away that the covariance, sigma xy, sigma sub xy, the further away it is from 0, the stronger the dependence there is. So let's look at then the definition of how we actually find the covariance. So x and y are going to be our random variables with a particular joint PDF of f of xy. Now I'm going, since I have more than one random variable here, I'm going to let the expected value of x be equal to mu sub x, just to shorten things up. Expected value of y is equal to mu sub y. We've seen this notation before. It's just convenient to write out to make things look a little bit nicer. So if I have a discrete random variables x and y, the covariance of x and y is equal to the expected value of, take x minus mu sub x, the mean of x, the expected value of x, that quantity times y minus the mu sub y. Notice again how this is similar to what we had with the variance, where we were actually looking at the expected value of x minus mu squared. So instead of having that squared there, we have an x minus mu x, and we have a y minus mu x. Now the way to find this is that since I have two random variables, I sum over all possible values that x and y can take on. And when am I summing? X minus mu x times y minus mu y times then the corresponding probability that you observe a particular x, you observe a particular value of y. When x and y are continuous, then we again replace the summations with integrals and slightly change then the meaning of what f of xy represents. So here's a question then for you, given this definition of the covariance. Suppose you wanted to find the covariance of x and x. How would you represent it up here? And what would it actually reduce down to? Well, that would be the expected value of x minus mu x, and then again, x minus mu x. In other words, it is the variance that we've seen before. Of course, you could do the same thing with y to show that too. Now, to actually find this expected value, rather than using the previous expression, what one most often actually uses is a shortcut expression, similar to what we saw with the variance. And one can show that the covariance for x and y is equal to the expected value of x times y minus mu sub x times mu sub y. Well, why? Let's just do a simple proof. Okay, so this expression in here is very similar to what we saw in a previous set of notes. This is like having this expression g of xy, so some function of our random variables x and y. And that quantity inside there, what we can do is multiply it all out. So that's what I do. We have x times y minus y times mu sub x minus x times mu sub y plus mu sub x times mu sub y. Now, similar to what we saw before when we had an expression like this, a times y plus b, and I wanted to find the expected value of that, where this was equal to a times expected value of x, expected value of y, excuse me, sorry for being messy here, a times expected value of y plus b. We've seen that before. We can distribute the expectation through the sum, and it all corresponds to working with the integrals. We can do exactly the same thing here. Also notice here how we have that constant factor out of the expected value. Again, it all deals with dealing with the integrals and stuff. If we're thinking in terms of continuous random variables, that is, same thing happens with the sums. And so we can always factor a constant out of an expected value. So what that means is let's distribute this expected value through. The expected value of xy minus mu sub x is now a constant, is the mean of x. It's going to be an actual number like 30, like we've seen before. So I can factor that out, and I get expected value of y there. Minus, again, mu sub y is going to be constant. I can factor that out, and I get the expected value of x right there. And lastly, I have the expected value of mu x times mu y. Or if you wanted to, you could factor out mu x, mu y, and now you have the expected value of 1. Well, what would you expect 1 to be on average? Well, it has to be 1. It's a constant. So with that then, well, what is the expected value of y? Well, in our notation, mu sub y, expected value of x is mu sub x. So look at what happens here. We have some nice simplifications. All of these terms here match up. It doesn't matter if you take mu x times mu y or mu y times mu x. It's like taking 30 times 40, which is equivalent to 40 times 30. And so then we have two of these cancel out, and this is what we get. And that's what we said were what we had originally. Okay. Now note that the expected value of x times y, generally speaking, will not be equal to mu sub x times mu sub y unless we have a particular condition hold. We'll talk about that later. Now, unfortunately, there's actually one problem with the covariance, and that is, well, it tells us if we have positive or negative dependence. And the farther you are from 0, the stronger the positive or negative dependence. It doesn't really give you a nice way to say, yes, I have, let's say, the strongest possible kind of dependence, meaning perfect dependence, perfect positive, perfect negative. It doesn't tell you that. And it can actually be hard to interpret because when you're working with a numerical scale for one problem, let's say college and high school GPAs, you can't compare that amount of dependence that you have there to some other problem that might be measured on a totally different numerical scale. So a fix to that problem is to rescale that covariance by dividing it by the standard deviation of the x and times the standard deviation of the y. When you do that, you have what's called the correlation coefficient. This correlation coefficient is always between -1 and +1. When you have a value of 0, and I'm going to use the Greek letter rho, that is not a P, that's the Greek letter rho to denote the correlation. Most people commonly do that. When the correlation between x and y is equal to 0, that means you have independence, just like what we had with the covariance. Now, for the correlation being greater than 0 means you have positive dependence. Correlation being less than 0 means you have negative dependence. And the closer you are to 1, the stronger the positive dependence. Where if you are actually at 1, that means you have, you can say, perfect positive dependence. Meaning that if you know x, you can get y. If you know y, you can get x. In terms of what a plot of what that will look like corresponding to what we had before, you would have something that looks like this. All the points will lie on a straight line. Let's say the line x equal y plus b times y. When you have a correlation that's getting closer and closer to -1, that means you have stronger and stronger negative dependence. And what that corresponds to then, if you have correlation coefficient equal to -1 itself, that means again you have a perfect negative dependence. In other words, related to the plot that we've seen before, you would have something that looks like this, where if you know x, you can get y. If you know y, you can get x. You know that perfectly. They're represented by simply a linear expression. So with that as background, this is what the actual correlation coefficient looks like. I take my covariance, I divide by the standard deviation for x, and the standard deviation for y. Where notice I'm using this shorthand notation to mean square root of the variance of x and the square root of the variance of y. Sometimes people will, instead of using that rho sub x, some people will use core parentheses x comma y and parentheses, the correlation between x and y. So let's take a look at an example. This goes back to our grades for 2 courses example that we've seen previously. Here's our probability distribution function. And to find the covariance between x and y, so we can understand the relationship between the math grade x and the stat grade y, I'm going to use this little shortcut expression that we saw before. I need to find the expected value of x times y. I need to find the expected value of x. And I need to find the expected value of y. So how do I find the expected value of x? Well, I go back to what we've seen before. I need to integrate over all my possible values of x, all my possible values of y. And what am I integrating here? X times the joint PDF. Or equivalently, if I take this part right here, this is equal to g of x. In other words, the marginal distribution for x itself that we saw previously when we were talking about joint PDFs. So I could do it that way. In fact, in my notes, I do find the expected value of x just using that itself. So now it's just a matter of using calculus. And in the end, the expected value of x, in other words, mu sub x, is equal to 7 divided by 12. To find the expected value of y, I can approach it in a similar manner, and I get 2/3, where I only show in this particular case working with the marginal PDF for y, which we again have found in previous set of notes. Now, to find the expected value of x times y, though, unfortunately, since I have both x and y there, I do need to work with that joint PDF and go through the integration. So I integrate from 0 to 1 with respect to x, integrate between 0 and 1 with respect to y. What am I integrating? X times y times f of xy. I go through the calculus steps, and I get 3/8. So now let's put this all together. My covariance of xy, in other words, sigma sub xy, is equal to the expected value of x times y, which is 3/8, minus the expected value of x, 7/12, times the expected value of y, which is 2/3. Go through the math, get negative 0.0139. So what this is saying is that there is actually negative dependence between x and y. How would I do all these calculations then in Sage? Remember, with respect to r, it's hard to do a double integral like what we need, so that's why I'm just going to focus on using Sage here. So to do this in Sage, I need to define my variables x and y. If I wanted to, not for sure why I put a comma there. Well, it's okay to do, you don't need to. I could have just done this, var quote, single quote or double quote, x space y, end quote. I define my PDF as I've done before. And then to find the expected value of x times y, well, what I do is I use the integral function twice. So inside here, I'm going to take the integral of x times y times f of xy. I'm going to integrate over x. It doesn't matter the order that you use. I'm going to integrate from 0 to 1. Then once I have that, and I get it in a symbolic format, then I immediately apply the integral function again with respect to y, integrate from 0 to 1. What do I get? 3/8, which is exactly as what I had when I used by hand expressions. To get the expected value of x, I do a similar thing, but now I just put x in there. And expected value of y, same thing, but only y in there. So then when I put all the components together, because I've saved them into EXY, EX, and EY, I get negative 1 over 72. And if I try to find a numerical value, I can use the round function as we've seen in the past. I get the negative 0.0139. Now, in this particular case, I could have worked with the direct formula or expression that I showed you at the very beginning to find the covariance of x and y, and Sage was able to go through all the calculus details and get what we needed. Okay, now to find the correlation coefficient, now I need to find the variance of x and also the variance of y. And again, often the easiest way to do that is to use these little shortcut formulas for the two variances. So I need to find the expected value of x squared. So I can find that. I can find that with respect to my joint PDF, like this. Or I can just take my marginal PDF that I have found previously and do the integration with respect to only x. The variance ends up being 19 over, expected value of x squared ends up being 19 divided by 45. Combine that with the expected value of x that we just found, 7/12. 19 divided by 45 minus 7/12 squared, get 0.0819 as my variance. I can go through similar steps as well to find the expected value of y squared, 23 divided by 45. Combine that with the expected value of y as well. The variance is 0.0667. So finally then, let's put all this together. Here's my covariance. I'm going to divide by the square root of the variance of x times the square root of the variance of y, and I get negative 0.1879. Okay, so what does this mean then? Again, this means I have a negative dependence between my math score and my stat score or grade. And what this is saying is since this isn't very close to 1 at all, it says that this is a relatively weak amount of dependence. So generally speaking, we would expect that as math grades go up, stat grades go down, and vice versa. But the dependence there is not very strong at all. To do these calculations in Sage with respect to the variance, please take a look at the approach that I took here. It just applies the same steps that we've seen now for other problems. Okay, so just to sum up, what we have developed here is a way to understand the relationship between two variables, to quantify it, to measure it. Where would this be useful? Well, as we just saw with that grades example, suppose we changed it slightly. We can think of, let's say, the prerequisite for our class that we're taking right now as, let's say, the X grade. The Y grade is the grade for our class right now. And if I have, let's say, a correlation of 1, then that says how you did in that prerequisite course is going to perfectly predict how you do now in our particular course that we're taking right now. So if you score, let's say, a 95% in, if you did very well in the prerequisite to our course, that means you're going to do very well in our particular course as well. In other words, high scores for the previous class means high scores for this particular class relative to, let's say, the distribution of scores. And that's key. And the reason why I say that is, let's say in your previous class, most of the grades ended up being between 80 and 100. And let's say in our particular class, all the grades end up being between 70 and 90. So if you got a 100 here, that means you're going to do high relative to that scale. What are some other examples? Well, humidity and temperature. We often, during the summer, we have high humidity, high temperature. During the winter, low temperature, low humidity. Well, we can quantify that using correlation. How about ACT score and SAT score? Again, you would expect those to be positively related. Winning percentage and the number of yards per game on offense for NFL teams, you would expect some correlation there as well. And this numerical measure helps us measure that. So with that then, that gives you a brief introduction to concepts like covariance and correlation that measures dependence between two random variables.